So, welcome everybody to today's mathematics class. As usual, please take a seat so we can get started. Right, so we started our adventures in calculus yesterday. We discussed sequences and limits of sequences, and today we'll continue this discussion with a special type of sequences that unfortunately is very useful in practice. Unfortunately, because it's a little bit more complex to handle, and we'll talk about series today. Before we do that, however, here's a quick look at a special sequence that at least you should know about. So in this video, talking about Euler's number, I discussed this sequence here, 1 plus x over n to the power of n, and I proved that this sequence converges. Now, I wouldn't expect you to be able to reproduce the proof, but what you should know is that this is a convergent sequence, and you should also know the limit of that sequence. And let's scroll right to the end here. So the limit of this sequence here, so you have it here, that is what we know as Euler's number, and we abbreviate that by a small e. So the number that is the limit of this sequence, that is called Euler's number. And in particular, the limit of this sequence for arbitrary x values in here, one can also show that this converges in general, and one can then show that it converges to e to the power of x. So this is the limit of this function. Or sometimes we'd also write this as exponential of x. All right, so from this video, that is the take-home message. That is what you should know. The limit of this sequence is Euler's number to the power of x. All right. Brief application of that. Pretty famous application is called continuous compounding. The idea here is that you make an investment, safe investment, you get a fixed interest rate on that. Your initial investment is C0, and after each year you get an interest rate of R added to that. So you have your original C0 plus interest rate times your original investment. That's what you have after the first year. Could also express this in this way here, 1 plus R times C0. And then of course if you wait 2 years, the interest that you got will also be invested. So you just let it all stay on your account and you let it grow. So after the second year you get C1 times 1 plus R for the same interest rate R, or 1 plus R squared C0. And of course you can see that after n years this has grown to this rate here, 1 plus R to the power of n times your original investment. And now this is what we call discrete compounding, because you receive your return on the investment each year in discrete time steps, once a year. Now you could ask, what if I would receive that interest not just once a year, but instead in monthly installments? So each month I will get a 1/12 of my yearly return. And then of course from that point on, that would also be reinvested, and for the rest of the year you would also gain on that. So after 1 year, this is what you would have, right? You will get R over 12 each month, and for 12 months, and each month you reinvest what you gain. Another question you could ask is, well, what if I make this smaller and smaller? What if I change to weekly or daily or hourly or per second? Make it as small as you want. And basically what this leads to is the question of what is the limit of this, as this m here goes to infinity. So M here is the number of periods per year, basically, that you have. And of course, you will now recognize this is exactly the sequence that converges to Euler's number. So the answer is, after 1 year, your investment will be e to the power of r, times what you originally invested, of course. And that is where, more or less naturally, this number shows up, or the sequence shows up. All right, so that's an application in finance. So much about Euler's sequence. We'll talk about Euler's number in other contexts later on. It will also show up in the context of series in just a minute. So let's talk about series. Formally, a series is just a sequence of a very special type. What you could do is, let's say you have a sequence, any sequence, then you could try to sum up that sequence, right? You could sum up the sequence elements starting at usually 0 or 1 or wherever you like, and sum up to some element n. This sum here is known as the nth partial sum of that sequence. And of course, you can again define a sequence that way, right? So you have a sequence defined by summing sequences. This Sn here forms a sequence, right? Each sequence element is a sum, and the number of elements that you sum up increases with each sequence element. A sequence of that type is called a series. And of course, you can ask the same questions that you can ask first for usual sequences. Does that thing converge? What might be the limit? Can I recognize whether it converges in an easy way? And that's just the questions that we want to answer about series here. Usually for series, there's a nice shorthand for the limit. What we do is we simply replace the n here by an infinity. So we sum up over all elements up to infinity. And that's just a shorthand for saying we're interested in the limit of these partial sums. Yeah, so if I take more and more sequence elements, will that converge? Will the sum converge to some finite value or not? Okay, if the series is divergent, again, we might have the case that the sum still goes to infinity or minus infinity, or it might jump around widely, as sequences also might do. And in that case, we, as a shorthand, write something like this sum is equal to infinity or minus infinity. The meaning behind this is actually, so precisely speaking, you would say the limit of that tends to infinity or minus infinity. And as with sequences, in that case, we would still say the series does not converge. Convergence always means the limit is finite. So it has a finite real number as its limit and not plus or minus infinity. All right. So basically a series is just a sequence, but it's a complicated sequence. And there are some special methods to investigate that sequence, and that's what we'll look at next. One remark that you should keep in mind is this one here. Oops. This one here. Of course, if those elements here will not get smaller at some point, then you sum up the same number over and over and over again, or something that's even greater than one number over and over again, and you couldn't expect that to go to some finite value, right? So whatever value you have, you add up another element of your sequence, and if that does not become smaller and smaller, then of course the sum of those will never converge. So that means if you want that to converge, you want to have a chance for that to be convergent, the summands need to be a sequence that has a limit of 0. Those need to get smaller and smaller and smaller. Otherwise, convergence will not happen. All right, so that's the first criterion. Usually you first take a quick look at that sequence of summands here, and if that does not converge, or if that does not converge to 0, then it is immediately clear that the series can converge. However, if that does converge, that doesn't mean the series must converge already. Yeah? There's more to that. Quick examples here. And those are also the prototypical series that you should remember, because most of the series that we'll talk about are in some way related to these prototypical series. And usually the way to compute the limit and to find out whether they are convergent is to try to reformulate them such that they take this form or another prototypical series form. There's just a handful of series you need to remember. One is the so-called geometric series. You will, or you might remember that this series is called the geometric sequence. So summing up the geometric sequence yields a geometric series. So basically that looks like this. You start with 1 plus q squared plus q to the third and so on. And we do know a formula for expressing these partial sums here. So if we sum this up to n, we've already discussed that formula. There's this closed expression here, right? So the partial sum is 1 minus q to the power of n plus 1 over 1 minus q. And now it's easy to see when this converges. Of course, if this part here goes to 0, then we have a chance for convergence. And then the limit is 1 over 1 minus q. And that happens exactly if the absolute value of q is strictly less than 1. If q is greater or equal to 1, then all these summands here are positive, and they grow. So they're far from going to 0, and that means the sum will diverge, and it will tend to infinity. And if we have something negative here, then the summands will grow and jump around widely, so the series will diverge without ever going to plus or minus infinity. Right? So that's the geometric series. And of course, this here, the conversion case, that's the most important one. So if this q here is less than 1 in absolute value, then the series does converge, and this is its limit. Another famous and important series called the harmonic series. Maybe you remember that this was called the harmonic sequence, but that's not that important. The series is more important because that's a prime example for a non-convergent series. This sequence here, 1 over k, of course, that converges, that goes to 0. Right? So this first criterion, the sequence of summands goes to 0, that is fulfilled, and still the harmonic series grows beyond every limit. I showed you how to prove that here. Basically, it's a clever grouping of the elements where you can show that this can get larger than any value you want. So this is a divergent series, and it tends to infinity. Right? Again, a series that is important in many, many examples, because many examples can be reformulated to something that looks like this. And if you can do that, then you know your series diverges. And oops, sorry, one more example. And here's where Euler's number shows up once again. This series here, sum of 1 over k factorial, that is called the Euler series. And that also converges, and we can show the limit of that is, again, Euler's number. So that would be another way to define Euler's number if you want to. In the video, I showed that using the sandwich theorem based on this definition here. Oops, on this definition here of Euler's number. Again, it's not important that you know all these details. You should be able to understand the principal idea behind that. And I wouldn't expect you to reproduce that in any way. I would expect you to know the series and its limit. And we'll encounter a series of that type again when we talk about differentiable functions later on. All right? So, Euler's series. And those are probably the 3 most important series that you should have in mind when trying to find out whether a series converges or not, and possibly trying to determine its limit. All right. Maybe let's do a few examples before we go on here. So let's take a quick look at, where do we start? Maybe this one here. Yep. So let me give you a quick example. This is from past exam, 2016 actually. And the question is, does the following series converge? And if so, what is its limit? And the series is given as 2 over n plus 2 factorial. So as usual, I'll give you a couple of minutes to take a look and see if you can find out whether that converges and what the limit might be if it converges. And as usual, to see whether you're done, please just give me quick feedback on tweetback. There's a question of whether that series converges. Just cast your vote yes or no. right, maybe let's take one more minute. All right, let's take a look at your results. And as you can see, most of you believe that the series does converge, and that is of course true. The series does converge. Let's take a quick look at why this is the case. So if you take a look at that series, that will probably remind you of one of the series that we have seen, and hopefully that is Euler's series. You will remember that looked like this here. 1 over k factorial from 0 to infinity, that's E. So this is almost the same thing. Two differences. We have a 2 here, and we have an n plus 2, not just an n here in the factorial. But we can deal with that. And of course, the 2 here in the numerator, that's easy. We can just take that out of the sum. So that's 2 times the sum. Right? And now what is the difference in the sum here? Well, in this case, if we consider this sum, we start with n equals 0, and n equals 0 corresponds to 1 over 0 plus 2 factorial. Right? So we have, as the first summand, 1 over 2 factorial. The next one is then for n equals 1. That will yield 1 over 3 factorial, 1 over 4 factorial, and so on. This sequence here, that starts with k equals 0, and k directly appears here in the denominator, so we start with 1 over 0 factorial. And by the way, remember 0 factorial is 1. Right, so that is well defined, 1 over 0 factorial. Then we have 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, and from that point on we have the same sequence. Right, so this part here is the same as this part here. Okay, so both are almost the same thing. Only difference is this blue sum here misses these 2 elements here. But of course we can easily correct that. We just can do this. We just replace that sum by 1 over n factorial. And now we have included these 2 elements, which are not included in the original sum. So we need to subtract them. Right, so what we do here is we now subtract minus 1 over 1 factorial and minus 1 over 0 factorial. Right? So altogether, this is again the red part. Okay, and now it's easy to compute the limit. Obviously this sum here, this is now Euler's number. So we get an E here. And well, 1 over 1 factorial is 1, and 1 over 0 factorial is also 1. So this is E minus 1 minus 1. So what we get is 2e minus 2 times minus 2, that's minus 4. Right, so that series does converge, and this here is the limit. All right, any questions about this one? Yes. So just to make sure that maybe I should add this here just to clarify how I mean that. So what I mean is the sum, this sum here, this extends only over this part, right? These here are not inside of the sum anymore. So they're not duplicated. Is that what you mean? Yes, sure, we do. So here's, those are minus 1 is minus 2, and 2 times minus 2 is minus 4. So I hopefully did that. But of course you're right, yeah. All right, so generally, the sum usually includes only what is immediately behind that summation sign. If I wanted to include all of these as well, I would use a notation like this. And I recommend you do the same. All right? Any other questions about this? So maybe as a general remark, you have probably seen by now, or you will see, that most of the sequence and series stuff really depends on knowledge of a few basic types of sequences and series and a handful of tricks to reformulate the expressions in a way such that they will be useful. And this is probably the main difference between the linear algebra that we've discussed before and the calculus that we are discussing now and will discuss until the end of the semester. Linear algebra is pretty abstract in many ways, but it is logical. It is all about concepts. If you understood the concepts, you should be able to apply them. In linear algebra, it's maybe not easy, but it should always be clear. If you understood the concept, it should always be clear what way, what recipe you would have to apply. Of course, the hard part is understanding the concepts. Yeah, I'm not saying this is easy. I'm just saying once you got those, the rest is not that hard anymore. With analysis, with calculus, of course, you also have to understand a couple of concepts. But the hard part here is that you have a large bag of tricks, a large bag of tools, and one of those might probably help, maybe even two, but there's no good way of telling which one to use. There are some hints, and over time you will hopefully get some intuitive feeling of what to try first, but that might also be horribly wrong. Right? In this case, of course, the hint is in this factorial expression, a sum over something that includes a factorial that could have to do something with the Euler series, so that would be worth a first try. But we also see examples where this doesn't work at all. Question? Yes, so the question is, will this also work with the root test? We'll discuss the root test hopefully today, in a couple of minutes. In this case, I would prefer the ratio test, I guess, but we'll see examples for those as well. The main difference, so if you haven't gotten to this point yet, the root test and the ratio test are methods that can be used to tell you whether a series converges or not in certain circumstances. It doesn't work every time, but in a lot of situations it does work. The downside is you'll only get information on whether the series converges or not. What you will not get is a limit. So if you have a problem about series, it's always worth closely reading the problem statement. If it says something like, determine the limits if possible, then you probably don't want to use the root test or the ratio test, because we need a limit, right? If it doesn't say that, that's probably a hint that root test or ratio tests are applicable here. And you don't need a limit, so You don't need these formulas. Could be easier. But again, we'll see examples of that. Does that answer the question? Good. So let's take a look at some more examples to complete our toolkit. Let's see, next one I want to tackle is this one here. So that is again from a 2016 exam. Let's call it 2016 too. Same question. Does the following series converge? If so, determine its limit. So there's your hint that actually none of these tests should be applied. So we want the sum from 1 to infinity over 4 times 2 to the power of n minus 1 over 5 to the power of n. Again, I'll give you a couple of minutes to figure that one out. And again, there's a little tweetback quiz to see whether it converges and maybe also what limit you get. Quick show of hands, who's done? Who needs more time? All right, let's give 1 more minute maybe. You're very undecided in this one. All right, let's take a look at your results. So we do have a winner, a very close one, 4/3. About 20% of you think this is not even convergent. About 20% think the limit is 0. So those are close seconds. And then some votes for the other limits. None of you liked 1/3. Interesting. All right, let's take a quick look at that one. And maybe a quick remark before we do that. I'm getting a lot of questions asking for when to use which tool here. I'll try to give you an idea about that today and also on Thursday. But maybe let's first go through that box of tricks that you need to have available. And I also try to point out how to recognize that might be one of the tricks you want to use here. So please give me some time to go into that huge question a little more. Hopefully by the end of this week, you'll have at least a vague intuition about what trick to use in what setting. All right, let's look at this one here. First thing, if the convergence in the limit is 0, that was almost second place. If you look at that, you should immediately recognize that all those summands that appear here are positive. That means you start your summation with a positive number and you only add positive numbers. You'll never be able to get back to 0. Right? So either that doesn't converge at all or it converges to something that is larger than 0, but it will not go to 0. No way. Okay, so I could immediately exclude that one. Now if you look at this formula here, sum over something to the power of n or n-1 or whatever similar thing, that should remind you of one of those prototypical series. In this case, that could be the geometric series. If you remember that, the geometric series looked like this. 0 to infinity, q to the power of k, q is some number, some constant. And if that converges, then it converges to 1 over 1 minus q, if that q is less than 1 in absolute values. Right, so something to a power, and the summation is over that power. Same thing here. We sum over n, and n is this power that appears here. We just need to see if we can reformulate it in a way such that it looks exactly like this. So let's give that a try. First problem is we have n here and n-1 here. Of course, we'd like the same power in both parts of our fraction, so that we can then write that as fraction to the power of something. That's easy to deal with in this case, because this 4 here, we can write this as 2 times 2. And we can just take one of those 2's and include it here. Right? So 2 times 2 to the power of n-1 is 2 to the power of n. Right? So what we do is we write this as sum from 1 to infinity, 2 times 2 to the power of n over 5 to the power of n. Then this other 2, that's just in the way, so we'll take this out. Yep. Sorry? This one. So what I did here in this step is I said 2 times 2 to the power of n minus 1 is 2 to the power of n minus 1 plus 1, right? So this 2 is 2 to the power of 1. And I just use laws of exponentials to combine those. So that's 2 to the power of n. That's where this here comes from. And I take this 2, I take this from the 4. Instead of 4, I write 2 times 2. One of those 2's is consumed in that way, and the other 2 is the one that remains. All right, so I'll take out that other 2 to get it out of the way. And then I have 2 over 5 to the power of n. And now I have almost the form that I need. This here is my q. So q is 2 over 5, and of course 2 over 5, that is less than 1. Between 0 and 1, so that should work. Only problem that I still have is I have a 1 here instead of a 0. Right, but we do know how to deal with that. We've seen that already. So just start from 0 and then subtract the sum that we've added that way. Okay, so now we have 2, and let's start our summation from 0 instead of from 1. And then subtract the one summand that we have added, and that's the summand for n equals 0. Right? So we add one summand by starting earlier, and then we subtract what we've just added. And of course we do this because these need to coincide so that we can apply our formula for the geometric series. And now we do just that. So this is 2 times formula for the geometric series, 1 over 1 minus q. Oops. So we have 1 over 1 minus, and q is 2 over 5 here. Minus, and 2 over 5 to the power of 0 is 1. Right, so now we just have to simplify that a little. Let's see. 1 minus 2 over 5, that is 3 over 5. So we get 2 times, let's see, 1 over 3 over 5 is 5 over 3 minus 1. 5 over 3 minus 1 is 2 over 3, so we get 2 times 2 over 3, and that is 4 over 3. So we can see that series converges because basically it's a geometric series, and the limit is 4 over 3. So close majority, but you were right. All right, any questions about this one? Yeah, so again, your hint in this case is first, I'm asking for the limit. So ratio root test won't do it. And then you're looking for a series that looks a little like the one you have here. And those powers, something to the power of n, that seems to suggest the geometric series might be a good idea. So that would be my first try. Reformulate that as a geometric series. All right, so we did that one. If there's no more questions about this one, let's move on to the next example. Again, one from 2016. And just in case you think this 2016 exam was particularly challenging, let me remind you that there are actually 2 exams. So part of these problems is from the original exam, part is from the retake. They were not all in the same exam, actually. But we covered almost all the tricks in that exam. All right, so here this is a sum from n equals 1 to infinity over 3 over 5n plus 2. Question is again, does this series converge? And if it converges, determine its limit. And again, there's a tweetback quiz asking you for your answer. Usual question, who's done? Who needs more time? Good, so we'll take one more minute. Finally, we're getting different answers here. Okay, so most of you think this does not converge. Some of you say it converged and the limit is 0. So let me quickly discuss that second option. What we are talking about here is this sum, right? So it's not about this sequence in here that does converge to 0. You're right there. But this here sums up elements, and none of these elements is 0. All of these elements are positive. They're getting smaller and smaller, but they're still positive. So you're starting with something that is positive. You add something positive on top of that, you will not be able to get a sum of 0. That will not happen. This sequence goes to 0. You're right there. But the sum of all these elements will not go to 0. It might converge, but it doesn't go to 0. Okay, the right answer is, of course, the one that gained 69%. It does not converge. Your hint in this case should be, well, this is, again, a series. And if you look at the summons, this is a fraction that is something like 1 over n, right? Here's an n. We also have this plus, and we have these additional factors. But we find some way to deal with that. So that is approximately 1 over n. And you will, or might remember, that this sum here, sum 1 over n from 1 to infinity, that is the harmonic series, and that diverges. Right? So the only question is, how can we prove that? How can we reformulate that to look like that? And what we need to do in this case is we don't need to exactly reformulate it to look like that. What we need to do is we need to show that it's bounded below by something that looks like that. Because if our sequence, if our sum is larger than this, and this is already infinity, then of course something that's larger is also infinity, can't converge. And that is what we often do in the context of harmonic series, or series that look like harmonic series. What we'd like to do is we'd like to get rid of the 3. That should be easy. We can just take the 3 out, right? Let's start with that. So that's 3 times 1 over 5n plus 2. The harder part is getting rid of these factors here. So we want the 5 out, and we want the plus 2 go away. We could factor out 1 over 5. But what about this plus 2 factor here? That makes life a little less nice. Well, what we could deal with is something like a plus 1 or a plus 2 or any constant number really. But once we factor out that 5, we'll have something like 2 over 5 in here. That's not very nice. So we need to make sure that we get an integer here when we factor out the 5. So this should be a multiple of 5, preferably. How can we get this done? Well, we'd like something like, maybe start with this, we'd like something like 1 over 5n plus 5, or plus 10, or plus 15, whatever, such that if we take out 1 over 5, we'll get a natural number. Well, what is the relation between those two here? What we did here, compared to this first expression, this top expression here, we increased the denominator. Here was 2, now it's larger by 3. It's 5 now, right? So when we increase the denominator, that means the whole expression can only be smaller, right? So the correct relation between those two would be, well, the top expression is greater or equal to this expression here, because this has an increased denominator, so it's smaller. So if we can now show that this tends to infinity, then of course anything that's larger, this here, also tends to infinity. And now here, we can actually take out that 1 over 5 factor, and that's what we're doing now. So that's the same as 3 times 1 over 5, and from 1 to infinity, 1 over n plus 1. Right, and now we're almost there. Just need to apply the same trick that we've applied numerous times. Remember this here, this expression starts at 1 over 1, so this is something like 1 over 1 plus 1 over 2 plus 1 over 3, and so on. And this expression here starts at, well, 1 over 2, right? 1 over 2, 1 over 3, 1 over 4, and so on. So the difference is this 1 over 1 here. So as before, what we are doing is we replace this by the expression that we know, the original harmonic series, and we just subtract the element that we've added. Let me write that as 1 over 1 maybe, like this, right? So here we included this 1 over 1 in that sum. That's not included here, so let's subtract it to make sure we have the same thing on both sides of the equation. Okay, and now of course we can say, well, this here, this goes to infinity. Subtracting 1 doesn't really change that, right? Infinity minus 1 is still infinity. And 3 over 5 times infinity is still infinity. So that all goes to infinity. So that means the series diverges and tends to infinity. Okay, and again, the hint that you should take here is we have an expression that looks remotely like 1 over n, so try reformulating it in that way. And for the harmonic series, we don't need to determine a limit, because there is no limit. All it takes is to bound it, so we need something that is smaller than the original expression and still goes to infinity. By the way, I think this was actually the hardest problem of this exam. Yes? How long does one, so how much time should it take you to solve this question? Good question. I don't remember all of the exam questions. I'd say with a little practice, you should get this done in 3 or 4 minutes, maybe. Does it seem realistic? It should seem realistic in a few weeks. It will, trust me. Okay, any more questions about this? So, almost done with my bag of tricks here. One more I'd like to show you. And I think this is not from one of the exams, actually. So let's just take this as an example here. Again, same question. Does the following series converge? If so, determine its limit. And the series looks like this. Sum from 1 to infinity. I'm using k here, well, it doesn't matter. 1 over k minus 1 over k plus 1. And notice this looks a lot like the harmonic series again, right? We have this 1 over k plus 1, almost the harmonic series. Problem here is, if you think of splitting that up, so you could say, well, I'm trying this here. This is the same thing as this sum minus this sum. That does not really work, right? Because both of those, this and this, will now go to infinity, so I get something like infinity minus infinity, and that could be everything. Right? So that doesn't help. Don't do that. Also, formally, it's wrong because you can't split it up because the two sequences don't converge. That only works if you have two convergent sequences. So you need something else here. Let's see if you can figure that out. And again, there's a quiz asking you for your answer on the limit or the convergence. Quick show of hands. Who has the result already? Who would like some more time? Good. Let's take one more minute then. It's almost a tie. All right. 37%, it does not converge. About 38%, the limit is 1. 13%, the limit is 0. You're trying to annoy me with that limit is 0, right? And a couple of votes for some of the other choices here. So most of you think the limit is 1, and almost the same number of things it does not converge. All right. Any idea of how to tackle this? That was a gut result. How did he do it? Yeah, exactly. That's the trick, right? So what is happening here is if you just try to write down the first couple of numbers, and actually that's something that I would do if I don't have any idea where to start. Try writing down a couple of numbers, and then maybe you see a pattern, maybe you get an idea of where this is going. So in this case, start with k equals 1, so we get 1 over 1 minus 1 over 2. The next summand is k equals 2, 1 over 2 minus 1 over 3. Then you get 1 over 3 minus 1 over 4, and so on. And what you can see, hopefully, is here's minus 1/2, here's plus 1/2, right? So that cancels out. Here's minus 1/3, here's plus 1/3. That cancels out. Here's minus 1 over 4, here we would get a plus 1 over 4. So that again cancels out. Only thing that stays is that 1 over 1. So what's happening here is those elements in the sum cancel each other out with the only exception of this here. A sum like this is known as a telescopic sum, by the way. Because very much like a telescope, you can just press on both ends and you get a very small sum left, right? So in this case, just this one stays. Formally, if you want to prove this in the right way, you would take a look at the partial sums. So let me just write that down, partial sums. So you'd say, if I just sum up to some index n, so that partial sum is from 1 to n instead of infinity, what do I get? Well, we pretty much figure that out. What we get is the 1 in the beginning, right, this here, that will stay. And of course, in this case, the last summand will also stay because there's nothing following it to cancel it out, right? So the last minus will also stay. Imagine we end it here, then we end up with the minus 1 over 4 because this next summand will not be part of our expression. So if we sum up until n, that last summand is 1 over n plus 1. So we get this expression. That's the partial sum for n. Everything in the middle cancels out. And then you remember the definition of this limit here. Limit of a series. Well, it's just the limit of the partial sums. So that's the same thing as the limit of the Sn's as n goes to infinity. Oh, and of course these Sn's, that limit is easily computed. Well, as n goes to infinity, this here goes to 0. So what we get is 1. And that will be the formally correct way of proving the limit is 1 here. All right, but I guess the hard part is figuring out this telescopic sum. And once you have that idea, the rest shouldn't be that hard anymore. All right, one final example, and that's again from the 2016 exam. Last one from that exam. I think that's the 4th, right? So that one looks a little weird, but it's actually easy, hopefully. N squared, 2n squared plus 2 over n squared plus 1 squared. So see if you can figure that one out. I'll set up a tweetback quiz in just a second. All right, who's done? Who wants more time? 2, 3, well, maybe 1 or 2 minutes. Let's give it 1 more minute. All right, so here's the results. 65% say it does not converge. About 11% say the limit is 0. About 17% say the limit is 1, and then there's a couple of votes for other limits as well. All right. Those of you who are right, it does not converge, of course. How did you come up with that answer? Any ideas? Yes. You simplify this part here? Uh-huh. And then? I think this is going in the right direction, but maybe let's make it a little bit more formal. So what we're going to do is we're looking at this expression here. And of course, you're right, we can simplify that expression quite a bit. First thing I would do is maybe divide by this n squared here. And maybe we can divide by another n squared. Let's see. Let me maybe write this in this way. So in this case, we can see there's an n squared, there's an n squared. So the highest degree in the numerator is n to the power of 4. Same is true for the denominator. We have an n squared squared here, right? So again, we get n to the power of 4 plus something. So let's divide by those highest degrees in both numerator and denominator, and I want that in white, please. Thanks. All right, so this is what I'm going to do. And what I get from this operation, well, of course, this n squared and n to the power of 4, and n to the power of 2 cancels out here. So I'm left with 2n squared plus 2 times 1 over n squared. And here in the denominator, I have this n squared plus 1, and I have that 2 times, so n squared plus 1 times m squared plus 1. And I have n to the power of 4 in the denominator. That's the same thing as 1 times n squared times 1 over n squared. So I can just take one of those factors into each of those two expressions. And that means what I get is, well, let me first complete the denominator. What I get in the denominator is 1 plus 1 over n squared times 1 plus 1 over n squared. Right? And in the numerator, I can do the same thing. I can take this in here. This cancels out, and here I get 2 over n squared. Right? So I have 2 plus 2 over n squared. And why am I doing all this? Well, the point is, if now n goes to infinity, what happens? Well, this here goes to 0, this here goes to 0, this here goes to 0. So the numerator goes to 2, and the denominator goes to 1 times 1. Right? So this whole expression goes to 2 over 1, or 2. So what we are doing, if we now consider the series, right, you will hopefully have seen I now consider just the summons. Of course, the question is about the series, not the summons. So my point is, I'm summing up over something that doesn't even go to 0. It goes to 2. Right? So the higher my n is, the closer I am to 2, and that means I'm summing up summands that are very close to 2. And of course, I can never expect that to stop anywhere. It will always grow and grow and grow and grow, so that whole thing will have to go to infinity. Right? So what that means is this will go to infinity because the sequence of summons does not go to 0. It goes to 2, not to 0. So that means the series is divergent. Right? I can only hope for convergence if the sequence of summons tends to 0, and this is not the case here. So that is the argument formally, and I think that's probably what you meant, more or less. Let's see you were on the right track. Okay, so that would be the argument. The sequence of summons does not tend to 0, and thus the series can't converge. And again, there's no clear recipe to see that, but of course, if there is no immediate way of seeing a series that is close to the one that you have in mind here, then it's either ratio test or root test. We'll discuss that on Thursday. Or it might be the case that this does not even go to 0, and that's at least worth a quick try. It's usually easy to figure out the limit of that summon sequence, and if it doesn't tend to 0, you're done. You can be sure that the series can converge. Right? So if you don't have any other immediate idea, that is worth a try. All right, that's it for today. As I said, we'll continue on Thursday, and then we'll talk about root tests and ratio tests to conclude that chapter.